Okay, today's March 28th, 2012. We're going to do lesson 3.3. The very first example says that the population of Barrie is modeled by this function. So this is a quadratic function, which we talked about before. Okay, it is squared. So we know that on a graph, this is going to make some kind of shape like this. Okay, it's a parabola when we go to graph this. Now, it tells us that P at T, which is this part here, is equal to the city's population. And T stands for time. So T is our variable. Remember, we've done this before where we wrote F at X. All they've done is change the letters. Our variable in the equation is no longer an X. We use T because it stands for time. And F, that usually stands for function, we use P for population. So this is really the same stuff we've done before. They're just using different letters to correspond to this question. So they've also told us that when T is 0, sorry, I forgot to write that other part in. That's the year 2000. Okay? When T equals 0, that is the population in the year 2000. So the very first question is, what is the population in the year 2000? So we're going to take this equation. P at T is equal to 0.5 T squared. I'll try to fix it for you. Plus 10T plus 300. Okay? Now, when T is 0, and we're in function form or function notation, we replace our T on the outside with the number 0. Okay? This is going to tell us what the population was in the year 2000. So what that means is all of the T's in the equation, we'll do it in red here, we're going to replace both of these numbers, or sorry, both of these variables with what number?
0.
That's right. So we're going to get 0, 0. So 0.5 times 0 squared plus 10 times 0 plus 300. Okay? Very good. So when we go to multiply all of this out, what is 0 squared, dude? Times 0.5? So this essentially just cancels itself out. It creates a 0. 10 times 0?
0.
That's right. So what is 0 plus 0 plus 300? That's right. So the population in the year 2000 is 300 in Barrie. Now it's probably in thousands, okay? I also just made up the name of the city. This is kind of arbitrary. But this is in thousands. We should have wrote that down. So technically the population is actually, in the year 2000, it is 300,000 people live in that city. Yeah, that's probably a good estimate of the city's population, okay? Now this function is telling us how it grows from year to year. So this is going to be an increasing graph, and the population is going to increase. Another thing I want to tie back to what we've done before is when I plug in 0 for the variable, and I'm graphing this, okay? So think about it. Normally, our F at X, or in this case P at T, is our Y when we're graphing, and our X, or in this case it's a T, this is our X when we go to graph something. So I'm going to make a small graph on the side here. I want to tie this to graphing. When we plug in T or X when it's at 0, what are we finding of that parabola? There's a specific name for it. Has to do with the intercept. That's right. We just found the y-intercept. So the y-intercept, and the reason that's the y-intercept, because along this line, that's when x is 0, or in this case, our t. T is our time, and y, or P at T, is our population. So in the year 2000, or in this case, when x is 0, the y-intercept is 300. So the next question, B of this, asks us, what will the population be in the year 2010? So in order to figure this out, we need to discover what we're going to plug in. Oh, I did make a small mistake. This should be a T. What we need to plug in for our variable T. Does anyone know what number I'd plug in for T? Benedict?
10.
Okay. Why would I plug the number 10 in if they're looking for the population in the year 2010? Okay, but why the number 10? Why not 2010? Okay, so the reason for this is because we're finding the difference. And what we can do here is, remember, we're going to make this like a ratio question. When T was equal to 0, we were in the year 2000. Okay? Now, 10 years have passed. We're now in the 2010. So they added 10. So we need to now add 10 to our t to figure out what t is equivalent to 2010. So in this case, it's just the number 10. So we're going to plug in the number 10 for each of the t's in this equation. Okay? So when we go to write this function out again, p at 10 is equal to 0.5 times 10 squared plus 10 times 10 plus 300. So we'll work this out together. 0.5, we're going to deal with the exponent first. What's 10 squared?
100.
Good. 10 times 10?
100. Plus 300.
Okay. How about 0.5 times 100?
50.
Good.
Whoa.
100 plus 300?
Oh, God. 400.
What's the final answer?
450.
Good. So, is the population just 450? What did we say the population? That's right. This is in thousands. So, in the year 2010, it's expected that the population of our city of Barrie was going to be 400,000 people. Okay? Could be goats, who knows? We're going to say people. Okay, third part about this question. We're still dealing with the exact same function. But this question asks us, when will the population reach 1,050,000 people? We have two variables here. Remember we talked about them. T stood for what? Time in what? What was it measured by? Years. Good. What was our other variable? P at T is what it stood for. What does it stand for? Okay. So, they've actually given us some information. Which of these variables have they supplied a number for?
T.
Really? So, in time, this is 1,050,000. Is that what they're asking us? Population. So, they gave us a population, which means we now need to replace the population in our equation with that number. When we do that, we can then solve for t. The goal is to figure out what year this will be. So, we're going to replace p at t with 1,050,000. I think you're close. Now, here's a quick question. Have I put this in properly? Why not? Okay. Someone finally pointed it out. Population was measured in thousands. So remember when we isolated 300, that actually stood for 300,000. If I draw too many zeros there, no. Okay, don't worry. So, what that means is when I plug in 1,050,000, I actually have to drop off the last three zeros. So the number I should be plugging in is 1,050. You're right, it was wrong. Because our population is measured in thousands. So we take 1,000 away from this, okay? Or in other words, we divide by 1,000. So this is the equation we're plugging in now. Now, in order to solve this, I need one side of the equation to be equal to 0. So I'm going to take the 1,050 and I'm going to move it to the other side of the equation. So we get 0. T stay there.
Would it be t equals?
No, it wouldn't, James.
We're going to work on that. All right. So we brought over 1,050. We've set this equal to 0 because that's the best way in order to factor it. It's the only way we're going to be able to solve this. So we have 0 is equal to 0.5 t squared plus 10t. Now, when we take 300 and subtract 1,050, anyone know what we're going to get?
750. 650.
Positive or negative?
Negative.
Good. Negative 750. Okay, very good. Now, I need to factor this question. Now, I know we're used to factoring when the variable is x, but it doesn't make a difference. We're going to factor when the variable is t. So the very first step to factoring it, what is it that we look for? Okay, so in this case, the greatest common factor, we actually want to get rid of the coefficient in front of the t. Okay? So this is going to be the greatest common factor. We're going to divide each of these, including the other side of the equation, by 0.5, okay? We're going to divide all of these by 0.5. So, when I divide 0 by 0.5, what do I get?
0.
0, that's right, okay? Oh, let's do that in black.
0 equals t squared.
It's equal to t squared
20.
double it.
1,500.
Good. Very good. Okay, now this is the important part. Remember, I told you guys you still need to know your stuff from the last chapter. So, in order to solve this, I need to factor it. So I'm going to take the factors of the first term. Remember, there's a 1 here. So we have 1t and 1t. And I need to take the factors of the last term. There are a lot of factors of 1,500. So obviously 1 in 1,500. 30 and 50 are one of them. And if you notice, they're actually going to be the two that work. Very good. Okay. So we know the factors. Now there's a whole bunch in between. Technically 10 goes into this times 150. There's a lot of different factors. But somebody already pointed out that these are the two we're going to be using. And we'll explain why. Remember, they need to add up to our middle term, which is positive 20t. So when I multiply, yeah, that's right. When I multiply this, we're going to get 30t and 50t. Now, in order to combine these to get 20, one of them will need to be negative, which is the 30. And let's double check now. If I make this 30 here negative, negative 30 times positive 150, does it give me negative 1,500? So, all right, so we know that works then. So we got to go put this into our brackets in our factored form. So we still have our 0 is equal to, these are our first terms. Now, do I need to put the 1 in front of the t? So we leave the t, okay? And we got to put them in opposite brackets. It doesn't really matter because the first terms are the same. So 1 will be negative 30, 1 will be positive 50. This is where the question gets tricky. We need this to equal 0, which means one of these brackets is going to have to be 0. Because in order to multiply to get 0, one of the numbers you multiply has to be 0. You can't multiply by any other number and end up with a 0. So what that means is we're going to split this equation. Benedict, yeah?
0 equals t minus 30.
That's right. We split it up.
0 equals t minus 50.
Good. And 0 equals t plus 50.
0 equals 30.
Okay.
0 equals negative 50.
Let's talk about this. So the reason we do this is I'm testing this question when the first bracket is equal to 0, and I'm testing the question when the second bracket is equal to 0. I'm going to solve for the variable, which is t in both of these. So I'm going to end up with two answers. When I move 30 to the other side of the equation, what does it become? That's right. So t is positive 30, or when we move 50 on the other side, negative 50. So let's talk about this. When we go backwards, way up again. So we got our answers. This is what our question was asking us. We discovered that t is equal to either negative 50 or positive 30. We have two answers. So our population, when t is equal to 0, sorry, that's the year 2000, we have to either add or subtract these numbers. So this is telling us that the population will be 1,050,000 people, either 50 years before the year 2000 or 30 years after. So that means either 1950 or in the year 2030. Now, we said this was a growing population. Yes, which means 1950 wouldn't make any sense. So in the year 2030, that's when the population will equal 1,050,000. Okay, so after we figured out all that information, we're going to tie this to a graph. Yeah, these two numbers, the 30 and the negative 50, are the x-intercepts. Okay, so we're actually going to put those on a graph as x-intercepts. I'm going to put up a new graph here. Those are our two x-intercepts. They told us that 30 and 0 and negative 50 and 0 would be our x-intercepts. That's what we found out as the year, as the years where our population would be 1,050,000. So what that means is I'm going to plot these 2 points. We have positive 30 and negative 50. So that means we have some parabola that goes down like this and up again. Okay? Now, in order, yes, to find everything else, we're going to need to find the vertex of this. So the vertex would also be the same as the axis of symmetry, or AOS. The axis of symmetry is R plus S divided by 2. Our R and S are the 2 x-intercepts. So we take 30 plus negative 50 and divide it by 2 to get the axis of symmetry. We get 20 over 2, negative 10. So what they're saying is the axis of symmetry, the line that cuts through the middle of this parabola, is right here at negative 10. That is also the same x value for the vertex. Okay? What we need to find out is the y value of the vertex. So we take our equation. Now remember, our equation was a little different because we had changed a few things. We'll jump back up here from before. This is the equation we're graphing right now. We're not graphing the original one. We're graphing the new equation. Okay? Our new equation is 0.5 t squared plus 10t minus 750. So when we go to put that out, we get 0.5 t squared plus 10t minus 750. Okay? So we need to find our y value. We're going to plug in negative 10 for the 2 x values or the 2 t's. Which means we get 0.5 times negative 10 squared plus 10 times negative 10 minus 750.
100.
Negative 10 squared will be 100. Negative 10 times 10. Negative 100 minus 750. 0.5 times 100? 50. Subtract 100. Subtract 750 gives us what? Anyone know?
650. Negative 800.
Negative 800. Now, I know that our access doesn't quite accommodate for that, so let's make them instead of go by tens, we're going to go by hundreds. 400, 600, 800, and 1,000. So, our x-intercept, or sorry, not our x-intercept, our vertex, the y value for our vertex is negative 10 and negative 800. So when we go to draw this, we have a parabola that comes up, and the slope gets very, very steep. So what that means is as the years pass, our parabola or our population is going to increase very, very quickly. This is how we would graph that question that we had. Okay? Remember, right here is when the population will be 1,050,000. Those are our 2 x-intercepts. We then found the axis of symmetry by using this equation, r plus s divided by 2. Once we had the axis of symmetry, we plug that number back into the original equation to find the y value of the vertex.
Go right there, please.
So our vertex is negative 10 and negative 800. That's everything together.
Yeah,